In this chapter, we're going to look at alcohols. Alcohols are basically water where one of the hydrogens have been replaced by an alkyl group. So essentially, you're looking for the hydroxyl group, that OH part of the water, which is the main functional group in your alcohol. So a pretty common functional group. You'll see this in a lot of natural compounds, see that in a lot of just synthetic compounds, compounds that we're going to use in lab. In this chapter, we'll also look at phenols. Phenols are alcohol groups attached to a benzene ring. Again, we'll see that having that benzene ring in close proximity yields a bunch of interesting properties. Regarding nomenclature, again, this is pretty straightforward compared to most of the other rules we've already seen. In the case of alcohols, we're going to have the all suffix that you see from that name. All right, so all of your alcohols will just have that all ending to let you know that that's the primary functional group. Okay, yeah, so you just again, just as a refresher, remember you want to identify your longest parent chain that includes the alcohol, and start numbering from the side closer to the alcohol group. Okay, so it's kind of a similar. Um, it's kind of a similar process as we saw earlier for alkenes and alkynes, of course, though, except here with alcohols. All right, so you can see that you want to select the parent chain as the longest continuous carbon chain with the alcohol group in it, okay, even if that is not the longest chain overall. You want to start numbering from the side closer to the alcohol group. Okay, now even we've seen that with things like alkenes and alkynes, sometimes we want to, if those were the only functional group, you start numbering closer to that side. But alcohol groups take priority over an alkene or alkyne. All right, and that's why the suffix of the name still has that all ending, even if you have an alkene or alkyne. So, for example, here we have an alkene present. So even though this is so if that alcohol group wasn't present, you'd call this a heptene, right, with 7 carbons, and you would start numbering from the right because that's where the alkene group is. But with the presence of that alcohol, this would be heptenol, and having that all suffix lets us know that we need to start numbering from the left, closer to where that alcohol group is. Okay. Now, in terms of assigning those locants, because alcohols aren't stuck to the beginning of a chain, you do have to assign a locant. They can be anywhere in the chain. An exception to this, of course, would be ethanol, right? With ethanol or methanol, your alcohol group has to be at the number 1 carbon, right? Once you get to 3 carbons or more, then, of course, that's where you can have you need to assign a locant to your alcohol group. Just like with alkenes and alkynes, of course, you can put that locant at the start of the name or right before the suffix of the name. So, for example, here we have 3-pentanol, or you could call this pentan-3-ol. All right. Personally, I find that calling it 3-pentanol is more common. But there are times when having that locant in the middle of the name is more convenient, especially if you have multiple functional groups. Okay. In the case of stereochemistry, if you have a chiral center and you need to assign R or S configurations, you put that at the start of the name in parentheses. Again, we've kind of seen this with other compounds, so this is still pretty straightforward compared to other nomenclature rules we've already seen in this course. Okay, in the case of a cyclic, of a ring compound, so you have a, cycloalkane with an alcohol group attached to it, that alcohol group's automatically at the 1 position, right? It's the primary functional group. So in the case of a cyclic alcohol where the alcohol group is the only substituent, you don't really need a locant here either. Okay, so just like with ethanol or or methanol, where that alcohol group's automatically at the one position, so you don't need to put a locant. Same thing here. So the example you can see up here, we've got cyclopentanol. You don't need to say one cyclopentanol. It's understood it's at the one position. For any other substituents, if you do have substituents in your ring, again, you don't need to put a locant for the alcohol group. It's automatically assumed to be at the number one position because it's the main functional group in the name. That's why it ends with all. But you can number everything else accordingly. Okay, so that's why in the example up here, the two methyl groups are the number 3 position. Okay. That being said, there are often common names in addition to these IUPAC names that you should be familiar with. I think two of the most common ones you probably see are isopropanol and tert-butanol. So isopropanol, also known as isopropyl alcohol, or IPA for short, is just 2-propanol. You essentially have that isopropyl group attached to your alcohol group. Okay, but of course, using IUPAC nomenclature, this is a propane, and that's at the number 2 position, so 2-propanol. Okay, with tert-butanol or tert-butyl alcohol, that's just 2-methyl-2-propanol. But again, you have a tert-butyl group attached to your OH group. Okay, we also have benzyl alcohol. Please note this is not the same as a phenol. Right, with a phenol, that OH group, that oxygen is directly attached to the carbon of the benzene ring. Here, the OH group is attached to the benzylic position. That's a carbon coming off the ring. Okay, so please note the difference there. Just like alkyl halides, our alcohols can be primary, secondary, or tertiary. So you look at that alpha carbon, the carbon that's attached to your alcohol group. And you see how many alkyl groups are attached to it. Now, if you have no alkyl groups, if you have only 3 hydrogens attached to that alpha carbon, it's just a methyl group. But depending on whether you have 1, 2, or 3 alkyl groups swapped out for hydrogens, your alcohol will be primary, secondary, or tertiary, respectively. Okay. Of course, we'll see that this is kind of important for steric reasons. We've already seen that in the case of alkyl halides, right? Depending on whether you have a primary or tertiary alkyl halide depends on whether it'll undergo an SN1 or SN2 mechanism, for example, right? And so we'll see that that's kind of important for alcohols as well. It also has implications for the way these alcohols oxidize. So we'll get into that later on in this chapter, but I'm just pointing out that again, it's important to be able to identify this readily. Okay. Regarding phenols, you can use phenol as a name itself, and that's the suffix for any derivative of that. So note that you can have substituents on that benzene ring. So for example, here we have a phenol group, and just like with with a cyclic alcohol, where that alcohol group's automatically at the 1 position, you can number your other substituents accordingly. Okay, so one common mistake a lot of students make, though, and you want to watch out for, is please note the difference between a phenol and cyclohexanol. All right, so a cyclohexanol will not have your 3 double bonds on that you see typically in your benzene ring. Okay, so as soon as you see that pattern of double bonds, please note that you have a phenol and it's not a cyclohexanol. Okay, and vice versa. If you don't see double bonds, then please note that your suffix is going to be cyclohexanol. Okay, so watch out for that, because that's a common mistake a lot of students make. But yeah, so again, notice that we kind of numbered this to give these substituents the smallest set of numbers. So we go clockwise here to put that nitro group at the 2 position, and that chloro would be at the 4 position no matter which direction you went in. But going clockwise gives a lower set of numbers. Okay, let's practice this. Go ahead and try naming this molecule. Please note that you've got an alkene functional group in there, so you're going to name this. This will have an enol suffix. All right. Go ahead and name that, and then also try drawing this molecule out. Okay, so feel free to pause this video as you figure that out. Okay, so if we are working through this problem, this top one here, you want to identify your longest carbon chain that contains your alcohol group and your alkene, since those are both going to be in the suffix of your name. All right, so that's probably going to be this carbon chain here. Right, so we've got 1, 2, 3, 4, 5, 6 carbons. So this is going to be a hexene-ol ending, right? So when we try to name this, we want to have locants for both of these functional groups. So now to make this a little bit simpler in terms of knowing which locant applies to which functional group, we might want to insert the locants into the name. Now I want to start numbering from this end because that's closer to that alcohol group. So that would be my 1 position, 2, 3, 4, oops, 5, and 6. So my alcohols are the 2 position, my alkenes are the 3 position. So this would be hex 3-ene and 2-ol. Oops, that's a hyphen there. Okay, hex 3-ene 2-ol. Oh, and so I guess you could also put the 3 in front there. So it'd be 3-hexene 2-ol, again with the 2 in front of that alcohol there. We have other substituents as well, of course. We have this isopropyl group at the 3 position. We have a chlorine and a bromine at the 5 position. So we want to, make a note of that. So in this case, at the we'd want to put those in alphabetical order. So it would go bromine and chlorine. So I guess it'd be 5 bromo. I may have put too much room for this, but we'll figure it out. 6, oh sorry, that's also 5. 5 chloro. And 3 isopropyl. Oh, I guess I put the right amount of space. Hexenol. Okay. And now we've got to look at stereochemistry concerns. In the case of our stereochemistry, or like R and S configurations for our chiral centers, 2 and 5 are both chiral centers. Okay, so we want to assign them R or S designation. So over here, that hydrogen that's not shown is pointing away. So we can use the priorities of these various groups to figure out if this is R or S. That oxygen is going to take top priority, followed by this carbon, which has 3 bonds to carbons. And then this would be, out of those 3 groups, this methyl group would have the lowest priority. So that's a counterclockwise designation. So that's going to be an S, chiral center. If we look at this carbon here, now there's no hydrogen here, so this methyl group is actually the lowest priority group. Out of the 3 groups attached to it, we have a carbon, we have a chlorine, we have a bromine, and they would go in that order, reverse order. Bromine's got the top priority as the heaviest of those elements. So bromine, then chlorine, then carbon. Okay, so if I were looking down at that methyl group, and I went from the bromine to the chlorine to that carbon, I would be going clockwise. It might be easier to build a little small model, just make a tetrahedral carbon and use different colored atoms, that you can assign to those groups to make it a little bit easier to see this. But for me, if I'm doing this in my head and I've got a 3-dimensional image of this in my head, if I'm looking down that towards that methyl group, these 3 groups would be going clockwise. So this is an R center. So when I'm writing out my name, this would be 2s 5r in parentheses. Okay. Now the other thing that we have to designate in terms of stereochemistry, of course, is that alkene. Now you can't use cis or trans here because there are 4 different groups, okay, attached to it. So you'd only use cis or trans if there were the same type of group on each of your carbons of your double bond. But that being said, we can assign priorities to groups and give them give this alkene an E or Z notation. So if I look at this double bonded carbon on the left, I've got an isopropyl group and I've got this group over here. Out of these two, this top group has higher priority because of that oxygen present, right? So this carbon is connected to an oxygen and another carbon. This one's connected to two carbons. So this one has a higher priority. Okay, so I'll just mark that here so I remember that. And out of these two groups, the hydrogen, of course, has a lower priority than this carbon. So this is the higher priority group. Okay, so both of these higher priority groups are on the same side, if you want to remember that designation. So this would be the Z alkene. Okay, I'm trying to remember now if I think I need to put this in parentheses. So I should probably double check that. But yeah, so that's what the uh, name should be. Right. For the second question, we want to, look at this. If you look at the end of this name, we've got cyclohexane diol. That tells us that our parent chain is actually a cyclohexane. So I'm going to just start off with the generic hexagon here. We're eventually going to draw the chair conformation of this, but let's just start off with the hexagon just to see where everything is. Now, we're told that we have a diol, which means that there are two alcohol groups on this, and they are at the 1 and 2 position. So normally if this were just cyclohexanol, you wouldn't need that 1, but since we're numbering two alcohol groups, you have to include the number 1 because you could, for example, have a 1,1 cyclohexane diol where they're both on the same carbon. Okay, so this is one of those weird times where you do have to put a 1 on your cyclohexanol. Anyway, so here we have cyclohexane diol, and so you can decide where you want your 1 and 2 position to be. So let's say this is 1 and this is 2, and it looks like it, in the case of our alcohol groups, we can see here that they're going to be cis. So let's say they're both pointing up, for example. I'm just going to assume that they're both pointing towards us. Okay, so I'm using solid wedges to designate that. Now we're told that there's also an isopropyl group at the 1 position. So if this alcohol group is pointing upwards, then this isopropyl group is pointing downwards, as I'm showing with the dashed wedge over here. Okay, so yeah, so those are the only substituents. So that's basically what that's going to look like. So now if we are drawing this as a chair conformation, and we want to draw this as the most stable chair conformation, we want to try to avoid having the bulkier of these groups at the at an axial position where they might strain with 1,3 diaxial strain. So instead, we might want to try drawing this isopropyl group equatorially. Okay, so when you draw your chair conformation, okay, think about how you want, out of these two positions, what you want where. Okay, so if you want your isopropyl group equatorially, that means that this alcohol group is axial. Okay, so that would be OH, and this is that group over there. But that then also means that this group, this alcohol group, would also be equatorial, right? Because if this is a down carbon with an up alcohol group, this will be at the equatorial position. So something like that. All right, so here you have the answer drawn a little bit more neatly than I have. Oh, and by the way, it looks like they've left off the EZ notation on this alkene here. They just used only the Kahn-Ingold prelog system. But to answer that earlier question, I double checked, and that EZ notation should be in parentheses. So, since this is a Zusammen or Z, that would be Z 2S5R, and the rest of the name accordingly. Okay, it looks like they also chose to put the locant for your alkene at the start of the name. Okay, so like I said, you could put it right before the ene part, or you could put it at the start here. But this is one of those situations where you have to put a number before the functional group within the name, because there's more than one functional group that you've got to assign a locant to. So I had mentioned earlier that alcohols in general are a pretty common functional group. Some simple alcohols that we see a lot include methanol, ethanol, and isopropanol. So you've probably already seen them quite a bit. We've seen methanol both as a solvent and even as kind of a good nucleophile. I mean, alcohols in general aren't super great nucleophiles, but we've seen methoxide, which is a derivative of methanol. You can make easily reacting methanol with sodium hydroxide. Ethanol, of course, a very common alcohol. Typically, what most people think of when they think of the word alcohol, and of course, a very common solvent as well. Isopropanol, also known as rubbing alcohol, you probably are familiar with that just for its use as an antiseptic. But again, very common solvent, used quite a bit. When I was in grad school, we actually used to run our base bath using isopropanol and potassium hydroxide. We'd make a potassium isopropoxide bath and use that to basically clean off a lot of our glassware. Okay, now one of the really neat things about that alcohol functional group in general is that it is capable of hydrogen bonding. All right, you've got an oxygen that's directly connected to a hydrogen, which meets the requirement for hydrogen bonding. So you can see that here we have three molecules that are similar in size, if not necessarily mass, but you can see that there's a significant increase in the boiling point for ethanol compared to the polar but non-hydrogen bonding chloroethane. And both of those, of course, have a significantly higher boiling point than ethane, which is nonpolar. Okay, so in addition to things like boiling point, this also affects solubility, right? So a lot of alcohols will, or at least the smaller ones, will dissolve readily in water due to this hydrogen bonding interaction. Once your alkyl group starts getting a little bit larger, now the non-polarity of that region might interfere with its ability to mix with water. So once you start getting into larger alcohols, they start getting a little bit more nonpolar. So that's something to watch out for. But typically, smaller alcohols are very miscible in water. Okay. So I think the cutoff there is about about 3 or 4 carbons. So if you have 3 or fewer carbons, you're typically going to have a soluble alcohol. And once you get to more than that, they start getting partially soluble and then finally insoluble. Okay. That's actually something to keep in mind for alcohols as antibacterial agents. You've probably seen that a lot of sanitizers, but like hand sanitizers or just general antiseptics are alcohols. Alcohols can disrupt the membrane in bacteria that sort of separate out the nonpolar and polar, the water-based parts of bacteria, because they have a polar alcohol group and a non-polar alkyl group. So typically, if you have a longer, sort of a mid-chain length for your alkyl group, that's where an alcohol is best at killing bacteria because of that sort of dual nature. So something to keep in mind there for selecting alcohols as, or the appropriateness of alcohols as antibacterial agents. Okay. Now, alcohols and phenols also have acidic protons. Now, we've probably seen when it comes to general alcohols, we've seen the acidity of the proton there. It's kind of similar, in a similar ballpark to water, right? Somewhere in that pK of around 15, 16 or so. And so as long as you have a base that's strong enough, it's easy enough to pluck off that proton and make the corresponding alkoxide ion. So for example, here ethanol will react with sodium hydride, which is a strong enough base to, your hydride will pluck off that proton and leave as hydrogen gas, and you'll correspondingly make sodium ethoxide, right? So that's the deprotonated version of your ethanol. So so typically alcohols are somewhere in that 15, somewhere between a 15 and 18 pKa. So definitely a little bit more acidic than obviously way more acidic than alkanes, more acidic than your than an amine. And you can kind of figure that out using just REO, right? Your oxygen's very electronegative compared to your nitrogen. They're both electronegative, but oxygen's more so, and so it's better at stabilizing that negative charge. Okay, and so, yeah. Now, the other thing to consider is resonance as well. So while alcohols, have that oxygen stabilizing that negative charge, and that oxygen is pretty electronegative, what helps even more is having that oxygen at an allelic position, okay, or a benzylic position, as is the case with a phenol. So in the case, phenol has a significantly lower pKa compared to similar alcohols, and the reason for this is that resonance structure. You can see that we have an allelic system here. That oxygen, which will pick up that negative charge when it gets deprotonated, that oxygen is in an allelic position here. So. Other things to consider, of course, with REO, induction. Consider if you have any electronegative groups nearby. You can see here by adding on some chlorines nearby, we've lowered the pKa of this ethanol. I think the orbital doesn't really come into effect here because we have, the oxygen is going to be sp3 hybridized regardless. So really that can't explain the difference there. We talked about solvation effects back in the chapter on acidity, and of course that comes into play here, especially when you're dealing with a primary versus a tertiary alcohol. I mean, don't memorize that like as a rule of thumb. Just kind of like look at your molecule, because it's possible to have a primary or secondary alcohol with very bulky alkyl groups. Something to keep in mind there. Yeah, so we actually, I believe back in that chapter, I think we even used ethanol and tert-butanol as examples of this. But you can see that there's a significant difference in their pKa's, and it's all just from that solvent effect. REO doesn't explain the difference between them, right? We still have an oxygen. It doesn't have any resonance structures. There's no induction effects, so it's really just the bulkiness of this terpyl group that stops, that makes it hard for something to come in and deprotonate the alcohol group. So you can see that here in this picture here. We have, because this is less sterically hindered in ethoxide, we have more solvent coming in stabilizing that negative charge, whereas when you do form it with the tert-butoxide, there's less of that stabilizing effect. Okay, so with that in mind, take a second, see if you can, you go through this example and rank these in order of increasing pKa, so strongest to weakest acid, use REO to help justify your answers. Okay, so let's go ahead and rank these according to REO. The A in REO refers to atom, and all of these have acidic protons on our oxygen, so the A is a moot point, right? They're all connected to an oxygen. So let's next look for resonance structures. So if we were to deprotonate here, would that, is that lone pair close enough to that double bond to allow it to exchange in resonance? And the answer is no, right? Because here, let me draw it separately here so we can so we can see how that works. So let's say I deprotonated that oxygen. Okay, if I were to have these swing down here, I would form a double bond here, which actually wouldn't be possible, right? Because we have two bonds to carbons here and a hydrogen, right? So that's going to a carbon, that's going to a hydrogen. There's nothing that really allows this bond to form. We'd have 5 bonds to this carbon, so resonance is not allowed here. Okay, so this, even though there's a double bond nearby, remember we need that lone pair to be in an allelic position, and that's not the case here. Now, for this guy over here, we do have a double bond, and that oxygen is in an allelic position to that double bond. So we could have resonance here. You could have these electrons swing down here, and these pi electrons swing to that nitrogen to get rid of that positive charge. So that actually is something that would engage in resonance. If you had this as a negative, if you had the anion here, this Zwitter ion would then disappear and be neutral. Okay, so I would say that this is probably our most acidic out of all of these. This would have the lowest pKa. All right. Next comes I for induction. So that would be this guy. So even though this double bonded oxygen is too far away to do any resonance, so we can get rid of that. There's no resonance there. This does have an inductive effect because of the electronegativity of that oxygen. So we'll put that at number 2. Out of these two, of course, then they don't have resonance or induction, and of course no orbital differences. These are all sp3 hybridized oxygens. But here we can see we've got these bulky ethyl groups nearby, so we see that sort of sterically hindering effect that prevents solvent coming in and stabilizing the negative charge on this oxide once it gets deprotonated. So this is going to be a worse acid than this one, or worse conjugate base at least. So I guess we would go 3 and 4 here. Okay, so let's start looking at some of the reactions involving alcohols. We'll first start looking at how we can make alcohols. We've already seen a few reactions that do this, so we'll kind of review those and look for some more. And then, of course, we'll later on look at some of the reactions alcohols themselves do. And again, we've seen some of those. We've seen alcohols as nucleophiles, for example, but we'll go through some other reactions there. Okay, so to make an alcohol, one easy way to do that we've seen already is through a substitution reaction. We can start off with an alkyl halide, where that halogen or that halide leaves as a very good leaving group. So as long as we get a an appropriate nucleophile, such as water or a hydroxide, we can get the corresponding alcohol. Okay, so depending on how you want to do this reaction, whether it's an SN1 or SN2 mechanism, that may dictate what you use as your nucleophile, right? So if you have a primary alkyl halide, which is more prone for SN2 due to that low steric hindrance, right? There's easy access for that nucleophile. We can see here we have sodium hydroxide. The negative charge on that hydroxide makes it a great nucleophile, and we can readily make this corresponding primary alcohol through an SN2 mechanism. Likewise, here we have a tertiary substrate, which forms a carbocation relatively easily, so we can use a weak nucleophile like water to do the SN1 mechanism as well. Okay, so now, could you use a strong nucleophile as well here? You could, but the thing you've got to watch out for with strong nucleophiles is that oftentimes they're also bases. And in the case of hydroxide, that is totally the case. Sodium hydroxide, as we know, is a strong base. And the problem with strong bases, especially with a tertiary substrate like this, is that we could also undergo an elimination reaction. Okay, so you not only will get your tertiary alcohol product, but you might also get a byproduct that is the resulting alkene. And so you'll get a lower yield of this alcohol because a significant yield will come from your alkene. And so to avoid that, we use a weaker nucleophile because it's not going to act as a base. Okay, we've seen that if we start off with an alkene, it's possible to make an alcohol through an addition reaction. Okay, so addition reactions will produce that. So we can use sulfuric acid. Dilute sulfuric acid will do an addition across that double bond. It'll follow Markovnikov's rule, but one thing you've got to watch out for is that since you're going to go through a carbocation intermediate, you have to consider any rearrangements there. Okay, if you want to avoid rearrangements, you could do an mercuration demercuration. So use mercury acetate and water, and then use sodium borohydride in the second step, and that'll give you the Markovnikov addition of your alcohol. And then if you want to do an anti-Markovnikov addition, you can do a hydroboration oxidation. So using a borane, you can, in one step use a borane and then subsequently use hydrogen peroxide and sodium hydroxide, and it will add the alcohol group to the less substituted carbon. Another way to prepare alcohols is through the reduction of a carbonyl. Now, carbonyls are carbons double bonded with oxygen. So we're talking about aldehydes and ketones here. Okay. Now, you're probably familiar with reduction and oxidation back from Gen Chem. Okay, so if you remember, we can assign oxidation states, sort of a way of bookkeeping how many electrons your molecule has, or an atom in your molecule has, by looking at how it's sharing those electrons. We can it's kind of like assigning a pretend charge to everything. You're treating everything as if it's ionic. So when you have a reduction, the oxidation state of your carbon's decreasing. Okay, so the way this happens is that your carbonyl, which has a double bond to oxygen, now winds up having only a single bond to an oxygen. So another way to look at it is that you're adding hydrogen across that double bond to reduce it into an alcohol. All right, so we'll see this in a couple of slides, but basically this is another relatively straightforward way to prepare an alcohol. Okay, so just to recap what oxidation entails, or how we assign oxidation numbers. This is probably a little slightly different way of looking at it than you might remember from Gen Chem. But if we were to look at methanol, okay, and we were to just break all of these bonds, homolytically, right? We treat them all as covalent bonds. We split them homolytically. We can see the 4 valence electrons that the oxygen, that the carbon has, and each of the 1 valence electrons the hydrogens have, and so on, right? You don't see the lone pairs in that oxygen, and of course we haven't split that bond there with the hydrogen there, but that would also have an appropriate number of valence electrons. Now, what about oxidation states, though, right? So we look at formal charges by breaking bonds homolytically. For when it comes to oxidation states, we're going to break the bonds heterolytically. We're going to treat it, as I said, like an ionic compound. So between carbon and oxygen, that oxygen is more electronegative. So instead of breaking that carbon-oxygen bond evenly, as you can see here, giving each of those atoms one of those 2 electrons, we're going to give both of those electrons to the oxygen. Okay? So when you do that, that essentially gives that oxygen an extra electron, so to speak, and gives it a negative charge. All right. Now, the oxidation state of that oxygen is going to be -2 because we're not showing it splitting with that hydrogen, but it would get an extra electron that way as well. But if we look at our carbon, you can see that it's got, when we break its bonds with the hydrogens, of course, the carbon picks up those electrons because it's more electronegative than hydrogen. And so we have 6 electrons on our carbon, and therefore it has a -2 oxidation state there. So our oxygen and our carbon both have -2 oxidation states, and our hydrogens each have a +1 oxidation state. So, and again, that makes sense. Like everything cancels out, so that you have an overall neutral molecule, as is the case. Please note that look at that in contrast to when we look at formal charges as opposed to oxidation states, where everything here is neutral from a formal charge standpoint. So with that in mind, look at how the oxidation state, the oxidation number of our carbon changes as we go through, various types of, molecule, or different, as we change the number of bonds to oxygen in our molecules, right? So if we look at methane here, carbon has only bonds to hydrogen, so it would actually have a -4 oxidation number here. Okay, so that's -4 on the carbon. When we have methanol, as we saw earlier, that oxidation state increases to -2. Okay, likewise, if we go to formaldehyde here, if we break these bonds to the oxygen heterolytically, that oxygen is going to take both of those electrons, both sets of electrons, but the carbon would take two electrons from the hydrogen. So oxygen, the carbon here has a 0 oxidation number. Okay, here when we have a carboxylic acid, there are 3 bonds to carbon, so and only 1 to a hydrogen. So the carbon here actually winds up having a positive oxidation state, a plus 2 oxidation number. And over here with 4 bonds to oxygens, carbon winds up being plus 4. So you can see that as we go through this progression of increasing bonds to oxygen and decreasing bonds to hydrogen, we wind up making the carbon more oxidized. All right, hence the name. And of course, if we go in the reverse direction, that's a reduction in oxidation number. So we can see that if we start off with an aldehyde here and convert it into an alcohol, we have a decrease in oxidation number, or a reduction, if you will. So, in order to carry out a reduction, we need a reducing agent. Essentially, what's going on here, right? We're adding a hydrogen to that oxygen, and you can't see it, but we're also adding a hydrogen to that carbon, right? So notice that this carbon now has 3 bonds to other heteroatoms, so there's a 4th bond to a hydrogen that's not shown. Okay, so we're adding hydrogen across that double bond, essentially. Okay, so if we're adding hydrogen across a double bond, well, we've already seen that reaction, right? We've seen hydrogenation of alkenes. Well, that also works for carbonyls. So we can use a metal catalyst like platinum, palladium, nickel, and hydrogen gas, and we'll do a syn addition of hydrogen across that double bond. Okay, now to carry this out, we often need high temperatures and high pressure. So depending on what else is on your alcohol, you might not like that method, just because if you have some sensitive functional groups there, that might lower your yield because it'll cause your product to decompose. So another way to do this, another good reducing agent we could use, is sodium borohydride. All right, hydride ions are pretty good reducing agents. They're good nucleophiles and bases as well, and that's kind of what happens here. It acts as a nucleophile. The carbonyl carbon is very electrophilic because it's connected to a very electronegative oxygen, so it's relatively electropositive. Okay, well, we'll spend an entire chapter talking about this next semester, but that's kind of the gist of it, right? That you'll notice that even in that chapter, like. Kind of what drives a lot of these reactions forward is that carbonyl carbon being a great site for a nucleophilic attack. So that's what happens here. Your hydride, being a great nucleophile, attacks that carbonyl carbon and shifts those electrons from that double bond up to the oxygen. Well, that in turn is now a nucleophile itself, and it can pick up, it can get protonated to get rid of that negative charge. Okay, and of course we'll see other reactions next semester where that can act as a nucleophile as well. But for now, you can get rid of that negative formal charge just by doing a simple proton transfer here. So you have something simple like water to act as an acid and donate a proton to that oxide, making an alcohol group, which is what we're trying to do. Lithium aluminium hydride is more reactive than sodium borohydride, but they both react in a very similar mechanism. They both provide a hydride, and that hydride attacks that carbonyl carbon and goes on to produce that alcohol. Okay. Now, due to that increase in reactivity, lithium aluminium hydride might be more or less appropriate for the reaction you're trying to do, depending on what substrate you're trying to use it on. Okay, so we'll talk a little bit more about that here. One thing to watch out for when you're using these reagents, lithium aluminium hydride will react violently with water. So it will carry out a side reaction there, and one, you're going to waste your lithium aluminium hydride. Two, you want to be careful of the explosiveness of that reaction. So that being said, we often use water as a proton source with the resulting ethoxide that we make. So you have to be careful about adding your lithium aluminum hydride and water in subsequent steps, and you want to use your lithium aluminum hydride as your limiting reagent in that first step for that reason. You don't want any excess lithium aluminum hydride around to react with your water in that second step, because again, that's a very violent reaction that you want to avoid. Okay, just for safety reasons. Okay, so in terms of selectivity here, um, this is, your hydride reagents will exclusively react with carbonyls. So you want to be careful if you have a a ketone or an aldehyde that you're using that also has an alkene functional group. Okay, because if you used your metal catalyst, you would reduce not only that carbonyl to an alcohol, but you would also reduce your alkene to an alkane. Okay, whereas if you use either of your hydride reagents, that won't be the case. You get only the alcohol, but your alkene remains intact. So that's something to keep in mind when, depending on what functional groups are present on your substrate. Okay, so basically your hydride, you can use various derivatives of your lithium aluminum hydride or sodium borohydride by swapping out the hydrogens on your metal center, or metalloid in the case of boron, with other groups. Okay, these can include alkoxide, they can include cyano groups, things that are very bulky, and again, that can kind of limit what they can do. Might make them milder in the case of a sterically hindered group, for example. All right, now with lithium aluminum hydride, I mentioned that that's going to be much more reactive. That sodium borohydride is, while reactive, is milder than your lithium aluminum hydride. And we see this with other carbonyl compounds. So far, when we've talked about carbonyls, we've focused more on ketones and aldehydes. But keep in mind that carbonyls can include carboxylic acids and derivatives of those, such as esters, for example. Okay, and again, we'll spend an entire chapter next semester talking about carboxylic acids and their derivatives, and the type of chemistry they'll do. And again, it centers around that carbonyl group. But we'll cross that bridge later. But my point here is that for now, understand that you can reduce carboxylic acids and esters down to alcohols using lithium aluminum hydride, whereas sodium borohydride will not do this. So watch out for any substrates you're using that have multiple functional groups, and be wary of what you're trying to make. Okay, so if a question has you starting off with something that has, let's say, a ketone and a carboxylic acid, but it only wants you to reduce the ketone and leave the carboxylic acid intact, then you might want to consider using sodium borohydride instead of lithium aluminum hydride. Okay. In terms of how the lithium aluminum hydride works with things like esters and so on, again, the mechanism starts off the same way. You have a hydride attacking your carbonyl carbon. And the thing to note here, though, is that instead of a hydrogen or R group, we have a decent leaving group in this alkoxy group here. So that actually gets kicked off when you're, basically instead of your oxide acting as being primed for a proton transfer and forming the alcohol directly, what happens first is that the double bond reforms and kicks off that leaving group. Okay, and now you've got an aldehyde. And at that point, of course, with a second equivalent of the lithium aluminum hydride, you can go on to form the corresponding alcohol. Okay, so please note that that we're using up two equivalents of hydride to do this, whereas before we were starting off with a carbonyl and just going directly to that alcohol, and you just needed one equivalent of hydride to accomplish that. Okay, so here you go, and so we can see that kind of highlighting. Look at all the functional groups we have present in this molecule. Okay, I'll point them out, but I'll let you look at it yourself first and take a stab at this. But notice that we start off with sodium borohydride. Ask yourself, what will that product look like? And then we use a stronger reducing agent, lithium aluminum hydride. What will that product look like? Okay, so pause this video and take a second to try and figure out the products. Okay, so notice that we have an ester over here. Okay, we have a ketone over here and an alkene over here. So we've got the milder sodium borohydride. Like neither of these reagents is going to reduce that alkene, right? That's going to stay intact in our product. Sodium borohydride will only reduce this ketone over here, but it'll leave this ester untouched. So our intermediate product here is going to have this ring still intact. So we have, it looks like a 7-membered ring there. Here, I'm just going to draw this. Actually, let's draw this up here. So the oxygen, and that goes there. So that stays intact. Sorry, this is a really lousy drawing. Sorry about that, guys. Sorry, that's not very well defined, but it's our 7-membered ring. Okay, so that's, yeah, if I put that double bond, that might make it a little bit easier to see what's going on. Okay, and then of course this gets converted into an alcohol group accordingly. All right, now this is a chiral center, of course, so you're actually going to get a racemic mixture of this. Is this, you can have a wedge or a dash here, it doesn't really matter, right? So yeah, so that's the product with sodium borohydride. Now with lithium aluminum hydride, then of course that will reduce this ester, and it'll, you'll break off over here. You're going to break this bond over here, and this will break off as and convert into its own alcohol group, and you'll turn this carbonyl into an alcohol group as well. Okay, so if you're having trouble seeing this, thinking about how this product will look, you could always number your carbons and plot that accordingly. But basically, we're going to have, looks like we start off with this. Okay, so I'm going to have that turn into an alcohol group. And here I've got 1, 2, 3, 4 atoms to get to that alcohol group. So 1, 2, 3, 4. Okay, and there's my double bond. Then carbon there. Yep. And so this is the product that we get after we react with lithium aluminum hydride. Okay. So when you have more than one alcohol, you can add a prefix to tell you how many alcohol groups there are. So if you have 2 alcohol groups, you have a diol. I think we've seen some examples already about that in terms of naming them. Let's look at how to prepare them. Well, if you have multiple carbonyl groups, typically as long as you have enough reducing agent present, you should be able to make, convert both of those into the appropriate alcohol groups and therefore make your diol. Now, other ways to make diols include addition reactions with reagents that do a dihydroxylation. So we've seen 2 ways of doing this back in our chapter 9, where we talked about addition reactions with alkenes. So if you recall, we can use a peroxy acid, and it will do an anti-dihydroxylation. Okay, it goes through an epoxide intermediate, if you recall. And that's why that oxygen on our epoxide blocks off one side, and so our oxygen nucleophile has to come in on the opposite side, and that's why we have an anti-addition there. In the case of osmium 8 oxide, that'll do a syn dihydroxylation. Both oxygens coordinate to that osmium center when you're forming your alcohol group. So both of these oxygens are at one point coordinated to the same metal center, and that's why they add on the same side of the alkene. Okay. Another way to make an alcohol group is to use a Grignard reagent. Now, Grignard reagents are very, very useful. We're going to see from a synthetic standpoint because they allow us to add on carbons. They essentially allow us to. They're a very useful way to extend a carbon skeleton. We've already seen some ways to do this, and so this is just another tool you can add to your synthetic arsenal. Okay, so what is a Grignard reagent? Well, in a Grignard reagent, we essentially insert a magnesium into an alkyl halide. All right, so we start off with an alkyl halide, we reflux it with magnesium, and our Grignard reagent is just a magnesium bonded to both your alkyl group and to your halogen. Now, magnesium, being a metal, gets oxidized into a magnesium 2 plus ion, which means that your alkyl group and your halide both have negative formal charges. Now, that's very important to note because in your alkyl halide, all right, if you were to break this heterolytically, your halogen's a leaving group, which would leave this as a carbocation. But in a Grignard reagent, we have a carb anion. Okay, and again, that's very significant because now a carb anion is a great nucleophile. Okay, so just as we used a hydride as a nucleophile with our lithium aluminum hydride and sodium borohydride, a Grignard reagent allows us to use our carb anion as a nucleophile and have that add on to a carbonyl and convert that carbonyl into an alcohol group. But again, in doing so, you're extending that carbon skeleton of your carbonyl into when you convert it into that alcohol. Okay, so let's so again this I kind of explained that all verbally, but here that kind of shows this kind of shows where we get our carb anion from. All right, and here's the mechanism again. So instead of your hydride ion attacking, we have our carb anion attacking our carbonyl carbon, and it again follows this similar mechanism. Now we make the corresponding, we have a negative formal charge on this oxygen, which then does a proton transfer and produces the alcohol that we're looking for. Okay, now something to watch out for with Grignard reagents is just like with lithium aluminum hydride, you want to avoid water being present. In addition to just the vigor of that reaction, the most important thing is you're going to waste your Grignard reagent. Your Grignard is a pretty strong base. It's going to pick up a proton, and it'll do that readily from water. And then you've just wasted your carb anion and just produced an alkane from it. So something to watch out for when you make a Grignard reagent. You want to make sure you keep it dry. Okay, so you probably so if you look at a Grignard lab that we do in lab, you'll probably notice in the procedure, like pretty early on in the procedure, you'll notice that there's a lot of reminders to keep your glassware dry, to take it fresh out of the oven, to make sure that it's you've baked off any water vapor that's condensed on it, and so on. So the reason is you want to make sure that all of your carb anion from your Grignard reagent reacts with your carbonyl compound and not with water. Okay, so here's some examples of Grignard reactions. So you can see here we have a Grignard reagent which is methyl magnesium bromide, and again that means we've got a methyl carb anion that's going to attach to that carbonyl carbon and convert the carbonyl oxygen into an alcohol group, as we see here. Okay, so here's another example. Here we have an ester, and as we saw earlier with lithium aluminum hydride, we kick off that methoxy group as a methanol byproduct, and just as we would use two equivalents of lithium aluminum hydride, two equivalents of hydride would add on there. Instead, we have two equivalents of Grignard adding two methyl groups to that carbonyl carbon when making the alcohol. Okay, so let's practice this. Have a look at these molecules here and see if you can make these corresponding products, but starting off with pieces that have 5 carbons or fewer. Okay, so if you've paused this and joined us again, you can see that here's how we would do that. So notice that we start off with an alkyl halide. This alkyl halide has 1, 2, 3, 4, 5 carbons. So again, that's the max you can get to. So we convert that into a Grignard reagent, and then we can have it attack this ketone over here, which has 1, 2, 3, 4, 5 carbons as well. And you can see that makes that product over there. Okay, so this alcohol group, that oxygen of that alcohol group used to be this carbonyl over here. Okay, over here we have an example of again we can have a similar alkyl halide that we convert into a Grignard reagent. We have it attack this aldehyde, and it makes this secondary alcohol over here. Okay. Now, have a look at this example here. So, why don't we, if we use this Grignard reagent over here with an alcohol group on it, why can't we use that to create this diol? Okay. Well, the problem is that your alcohol group that's in your Grignard reagent is also acidic. It's a proton source, right? That's protic. It can provide a hydrogen to another equivalent of Grignard reagent. And so essentially your Grignard reagent will react with your Grignard reagent, right? You'll have this carbanion, reacting, being sort of converted into an alkane, and you'll just get propanol as a byproduct before it can react with this carbonyl. So that's something to watch out for. Okay, so that being said, what if we do want to make a product like this? How can we stop? How can we prevent an alcohol from reacting? Okay, and so to do this, we use what are called protecting groups. These are groups that we temporarily swap out our alcohol for, that we can then swap back in once the reaction is over. Okay, we'll look at this phenomenon in other chapters as well. This is an issue that you often run into in synthesis when you want one functional group to react, but not another, or you need things to react in a particular order. To a certain extent, you can control this by choosing reagents, such as, for example, choosing sodium borohydride instead of lithium borohydride, as we saw earlier. But in this situation, we can get around that, right? Your Grignard reagent is going to react with that alcohol group. So we need to swap it out for some protecting group. So that's essentially how that works. We swap out our alcohol group for a protecting group that is unreactive. We then make our Grignard reagent and do our regular Grignard reaction, make the alcohol that we want, and then we deprotect it. We convert that protecting group back into an alcohol group, and there's that product, that diol that we wanted. Okay, so what is this protecting group? What are some candidates for that? Typically, we use a trimethylsilyl ether. So essentially, we have, it's typically abbreviated as TMS, or trimethylsilyl group. So you essentially use your alcohol as a nucleophile, and it basically forms, kicks off a chlorine group here. It helps to have an amine present, because then you can get this to sort of crash out of solution as an ammonium salt. But basically, that nucleophile reacts with your trimethylsilyl chloride, and it basically tacks on that TMS group to that oxygen. Okay, and this is relatively stable. This will not, since you don't have a proton on that oxygen anymore, this will not be acidic anymore. Okay, the other nice thing about about how this happens, why do we use a silicon as opposed to a carbon? The larger silicon atom allows for that nucleophilic attack from your alcohol to make that product. Okay, if that were carbon, this would be, you've got a tertiary carbon here. We know that that's not good for an SN2 mechanism. Okay, how do we deprotect a TMS group? How do we deprotect that alcohol, or make that alcohol back again? Well, to do that, we can remove that with either acid or with fluoride. A good source of fluoride is TBAF, or tetrabutyl ammonium fluoride. So to run through the whole process here, if you have that alcohol group that you don't want to react with your Grignard reagent, you protect it using TMS chloride and an amine, like tetraethylammonium here, or tetraethylamine here, and that swaps out that hydrogen for that TMS group, as you can see here. Okay, we get a precipitate of triethylammonium chloride, and then you can carry out your Grignard reaction, as you can see here. You make that corresponding alcohol group, and then of course you want to get rid of your TMS group. You want to deprotect it. So we react with TBAF, and we swap that back out for an alcohol. Okay, so I mentioned earlier that phenols are very good, as compared to other alcohols, are pretty good acids, and that makes phenols pretty useful from in terms of that their chemical properties. So how do we make phenols? Well, we produce a lot of it, and we typically start off with benzene or benzene derivatives, and we can accordingly uh, go through a we can oxidize it relatively easily. If you remember back in the chapter 11, we talked about radicals. If you have cumene, that benzylic position is very prone to oxidation due to the stability of that benzylic position or the radicals that you form in that benzylic position. And so if we make the corresponding hydroperoxide, it's possible then to pretty easily convert that into the corresponding phenol. Okay. All right. Uh, let's look at some reactions that alcohols themselves take part in. We've seen that it's pretty useful in a lot of substitution reactions. Of course, the alcohol group is not a good leaving group on its own, so it sometimes helps to carry it out under acidic conditions. We protonate our alcohol and then makes it a better leaving group. It leaves as water. Okay, and then the resulting carbocation is readily attacked by a nucleophile. So it's really good for an SN1 mechanism in that sense. Okay, in the case of an SN2 mechanism, though, again you have to make sure that alcohol, it's not a good leaving group on its own, so it always helps to protonate it to before you have your nucleophile come in and kick off that leaving group. Okay. Another thing to note for trying to do a SN2 mechanism, or helps something that might help make your alcohol leave a little bit more easily, is to use zinc chloride as your reagent if you're trying to swap out your alcohol group for a chlorine. So you can see here that if we use zinc chloride, the zinc winds up being a Lewis acid and coordinates to the oxygen, and again that helps that oxygen leave a little bit more easily. Okay, and then of course our chloride nucleophile can come in and swap out that alcohol for that chlorine. Okay. So we've also seen other leaving groups, such as toslate groups, that are pretty good. So if you swap out your alcohol for a toslate using tosyl chloride and pyridine, so it's very similar to what we saw with protecting our alcohol group with TMS. Instead, here we're using a toslate, but the mechanism by which we make that toslate is very similar, right? We use pyridine, and we get a precipitate of pyridinium chloride, and we get the hydrogen there swapped out for our tosyl group. Okay, so now we have a toslate, and this is a great leaving group. So we can do our SN2 mechanism here. Our nucleophile comes in, kicks off that leaving group, and makes the product we want. All right. Another reaction we can do to convert our alcohol into an alkyl chloride, like we saw with zinc chloride, is we can use thionyl chloride. That's SOCl2. Okay, so our alcohol isn't, again, our alcohol is a bad leaving group, but it can coordinate to our sulfur in our thionyl chloride. Okay, and make this corresponding intermediate. And if having a base like pyridine present is useful for plucking off a hydrogen and later on a chloride. We'd get a precipitate of pyridinium chloride. It's just shown as chloride here, but again, the pyridine helps with that. When we go through this intermediate, we can sort of eliminate that that sulfur and those two oxygens as sulfur dioxide. Now, this is a gas, so this bubbling away kind of drives this forward from a Le Chatelier's principle standpoint. If this was an equilibrium, you can see that it's not going to be at equilibrium very long. It's going to be driven towards the product side because of the loss of that sulfur dioxide gas. Okay, but that's essentially what happens. This is a great leaving group now. And again, what drives it forward is the fact that it can quickly convert an SO2. Okay. Another way to add on a halogen, in this case a bromine, is to use PBr3 or phosphorus tribromide. Okay, so very similar to what we just saw with thionyl chloride, our poor leaving group of an alcohol is still a decent nucleophile, or good enough a nucleophile to attack that phosphorus, right? We've got that large phosphorus atom, and the alcohol donates a lone pair to that phosphorus, creates this intermediate. Again, this is a great leaving group now. So our nucleophile comes in, kicks that off, and we wind up getting this as our leaving group here. Okay, so that in mind, let's try a couple of these practice problems out. Ask yourself, what are the reagents we need to go from this starting material to each of the intermediates we see here. All right, so notice that we start off with an alcohol and we're converting it into a toslate. So we remember to do that, we need tosyl chloride and pyridine, right? We need to have that base present to help. We lose pyridinium chloride in the process, but that swaps out this hydrogen for our tosyl group and makes this a tosylate. Now, notice that we go from having this toslate into this alcohol, and notice the stereochemistry being inverted. Notice the stereochemistry being inverted there. So that tells us an SN2 mechanism is probably happening. So we have our alcohol coming in, and having our our OH group coming in. So we probably use a strong nucleophile. So you could use a let's say sodium hydroxide here. So our hydroxide ion is our nucleophile. It kicks off our toslate, which is a good leaving group, and again, that's our SN2 mechanism. Okay. Now we have an alcohol again, and we want to swap it out for a chlorine. Okay, and notice the inversion of stereochemistry again here. Of course, though, this is not a good leaving group, and if we did this using, let's say, HCl, we wouldn't get this stereochemistry exclusively. We'd get a racemic mixture because we'd go through a carbocation intermediate, right? So how do we encourage just the inversion product? Well, remember, if you use something like thionyl chloride, something that converts this into a better leaving group, and encourages the chlorine to come in and do that SN2 mechanism, that would produce this product that we see here. All right, alcohols, of course, as we've seen, can be promoted into better leaving groups, and as such, if we use a base instead of a nucleophile, we can then do elimination reactions instead of substitution reactions. Okay, you want to, typically you'll see this undergo an E1 mechanism. The problem with an E2 mechanism, since we have a strong base present, you don't want that to, and since you need an acid to promote this as well, if you have a strong acid and a strong base, it'd probably just react with each other instead of with your alcohol. So typically, you'd prefer to have this react with your acid, form your carbocation, and then get a weak enough base. A weak base would be sufficient then to get this to convert into the corresponding alkene. Okay, instead of having a stronger base which initiates the reaction, which again wouldn't be likely because this is not a very good leaving group. Okay, so of course then with alkenes, when we do elimination reactions like this, you have options for where that double bond can form. Do you get a Zaitsev or a Hofmann product? Okay, so keep in mind how that forms and which ones, under what conditions you're making those. Okay. Of course, if you convert your alcohol into a better leaving group, then it is possible to do an E2 mechanism. So you can see here we tosylate our alcohol and convert it into the alkene using sodium ethoxide as our strong base. Okay. This is a very symmetrical substrate, so we're going to get this alkene, regardless. There's no Zaitsev or Hofmann product here. But again, think about the base you're using for regio-specific reasons, right? So think about using sodium ethoxide to get your Zaitsev product versus a bulkier base like sodium tert butoxide, which might give you the Hofmann product. Okay. why would you want to use the E2 elimination instead of E1? Well, remember, with E1, you're going through your carbocation intermediate, and that carbocation can rearrange, and you might get different products. So be wary of that. Be wary of rearrangement products that you might get. So with E2 mechanisms, you don't have to worry about rearrangement. So since the base is initiating it, you're not going through that carbocation intermediate. It all happens in one step. So be wary of that. Okay, we've looked at how to turn carbonyls into alcohols through reduction. Let's look at the opposite process. Let's look at how to convert alcohols into carbonyls using oxidation. So of course now instead of using a reducing agent, we're going to use an oxidizing agent. Okay, there are pathways for our oxidation that depend on the type of alcohol you begin with. So if you take a primary alcohol and oxidize it, you remove one of the hydrogens on that alpha carbon, and of course you remove the hydrogen on that alcohol group and form the double bond between the two. But your carbon, which is now carbonyl carbon, still has a hydrogen on it. So we have an aldehyde. Okay. Now this aldehyde can be further oxidized into a carboxylic acid. Now this is possible because we used a primary alcohol. What if we used a secondary alcohol? Well, with a secondary alcohol, we'd again remove this hydrogen and the hydrogen on our oxygen, and we'd make a corresponding ketone. But please note that there's no longer a hydrogen here, and we kind of stop here. We stop at that ketone stage. Okay. So note that we get a ketone, first of all, not an aldehyde, because we have another alkyl group here instead of a hydrogen. But I guess the more important thing to realize is that we don't oxidize this further. Okay, you don't make an ester out of this. It just actually stops at the ketone. Okay. In the case of a tertiary alcohol, well, there's no oxidation at all, because again, for oxidation to occur, you need to remove a hydrogen from this alpha carbon, and there's no hydrogen to remove. Okay, so tertiary alcohols are unreactive when it comes to oxidation. So what kind of oxidizing agents can we use? Well, a common one you'll come across is chromic acid, which you can make from multiple, there are multiple ways to make it. You could start off with chromium 6 oxide, sometimes called chromium trioxide, it's a common name there, or you could use sodium dichromate, and in both cases you can convert those into chromic acid relatively easily. Okay, so please note that, by the way, you might not see chromic acid listed as a reagent. You might see chromium 6 oxide or sodium dichromate and sulfuric acid as your reagents. Okay, so watch out for that. But just know that in general, your chromium is going to be an oxidizing agent here. Okay. So what happens then with our chromic acid and our alcohol? The mechanism involves two main steps. So basically, your alcohol will react with your chromic acid to make an chromate ester, and then this will react with water under an E2 mechanism. And again, this is kind of a good leaving group here. But basically, your water acts as a base, plucks off this hydrogen on your alpha carbon, and allows that double bond to form that carbonyl that we're looking for. Okay, so typically chromic acid is a strong enough oxidizing agent that it will not stop at the aldehyde step for the oxidation of a primary alcohol. Your primary alcohol will go all the way to a carboxylic acid. Okay, so if you want to stop at the aldehyde, you've got to consider a different oxidizing agent. Okay, so we had a similar type of problem back with hydrogenation, actually. If you recall, when we wanted to convert alkynes to alkenes, if we used a metal catalyst and hydrogen gas, we wouldn't be able to stop at the alkene, right? It would go all the way to the alkane. If we wanted to stop at the alkene, we had to use a poisoned catalyst. Well, like Lindlar's, for example. Well, we kind of have a similar process here. Basically, to stop at the aldehyde step, we're going to use pyridinium chlorochromate, often abbreviated as PCC. Okay, so this is made using pyridine, chromium 6 oxide, and hydrochloric acid, but this winds up being mild enough to stop at the aldehyde. It does not continue on to the carboxylic acid. Okay. Um, if you see methylene chloride listed, please note that the methylene chloride is a common solvent used for this reaction too. Okay, so if you see that in there, please note that methylene chloride is not a reactant per se; it's just a solvent here. All right. So yeah, if you have a secondary alcohol, of course, then it doesn't really matter what oxidizing agent you use. It's going to produce the ketone and stop there, right? You're not going to oxidize it further. So it doesn't matter whether you use PCC or you use even a stronger oxidizing agent. It's going to stop at the ketone. All right, let's go ahead and try a practice problem with this. So predict the products for the following reaction. So it looks like here you've got chromic acid here. So what's it going to oxidize? Well, we have a secondary alcohol here, we have a primary alcohol, and over here we have an aldehyde. Remember, chromic acid is a strong oxidizing agent. It will oxidize a primary alcohol all the way to a carboxylic acid. And any aldehydes will also get oxidized all the way to a carboxylic acid. Secondary alcohol, of course, will get oxidized just to a ketone and will stop there. So here's our product accordingly. So notice that this aldehyde gets oxidized further. This alcohol gets oxidized all the way to that carboxylic acid, and of course our secondary alcohol here gets oxidized to a ketone. Okay, so we've been looking at, this is obviously very useful from a synthetic standpoint. This process happens in a lot of natural systems as well. We see this a lot in biochemistry. And so you have, reducing and oxidizing agents present in a lot of biochemical pathways. Okay, so NADH is probably a common one. If you've taken biology before or biochemistry, you've probably heard of that as a common reducing agent there. Okay. So yeah, so you have usually a system between NADH and NAD plus, and that's oftentimes these are catalyzed by enzymes. Okay, so this is a very big part of metabolism, for example. So again, if you've taken a biology course or a biochemistry course where you've looked at the Krebs cycle or the citric acid cycle, you will see that this is a big part of that pathway. All right. Now, while we looked at the oxidation of primary and secondary alcohols, note that tertiary alcohols do not oxidize because they don't have an alpha proton. Well, for that same reason, phenols, you'd expect a phenol to also be unreactive, right? You look at your carbon, your alpha carbon, you're like, well, there's no hydrogen there to pluck off to form a double bond between the carbon and the oxygen. However, it turns out that due to that sort of benzylic position of that oxygen, you are able to oxidize this pretty readily. Okay, so due to that allelic sort of system. So what happens is with an oxidizing agent, such as any chromic acid, so if you use sodium dichromate again, you wind up making benzoquinone as an intermediate, which can then be converted into hydroquinone relatively easily. Okay, so you can you can restore. So notice that in benzoquinone you lose aromaticity in this ring, though you still have a conjugated pi system, so it's not completely destabilized. Okay, that's why this is kind of allowed, even though typically most reactions that break the aromatic system in your benzene ring are typically not good. Typically those reactions don't happen, right? We don't see a standard substitution reaction, for example, with a benzene ring, either with an alcohol or a halide leaving group, right? Just because you're not going to, that would involve that benzene losing aromaticity, right? You're going to try to form a carbocation at that sp2 carbon, and it's generally not good. Instead, though, here we do form that benzoquinone, and that's okay. Again, that's relatively stable. Okay, and we'll talk more about that next semester. We'll look at these conjugated pi systems and see why we get stability from that. And of course, we'll understand how aromaticity itself works a little bit more. But in any case, this can then be converted into hydroquinone, which is essentially sort of a diphenol. And note that we restore aromaticity. We restore that benzene ring in the process. Okay, so they're very the stability of these types of molecules is inherent. We'll see these quite often in nature because of their stability. Okay. So basically, you'll see these types of molecules used quite a lot in natural process and biological processes. Again, so for example, in cellular in respiration, you'll see ubiquinone used quite a bit there as well. Okay, so let's talk a little bit about the use of alcohols in syntheses in general. So we've kind of alluded to this in various parts of this chapter. Let's kind of bring that together with some of the stuff we've already seen. Okay, I kind of already pointed out some similarities between alcohol oxidation and the change in unsaturation, degrees of unsaturation for carbon-carbon bonds, right? So you can go from alkynes to alkenes to alkanes, and stop along the way depending on what reagents you use. And I pointed out you kind of do this as well with alcohol oxidation, right? If you can take a primary alcohol to a carboxylic acid, but you could stop along the way using PCC, for example. Okay, so please note, and of course note that you can go backwards along this pathway as well. It's not only in terms of adding across those double bonds to get to an alkane, but you can also work backwards using halogenation and elimination reactions to get the less saturated or the more unsaturated compounds along the way. So in the same way, we can use hydride sources like lithium aluminum hydride or sodium borohydride to reduce our carbonyl groups down to alcohols as well. Okay, so essentially we could combine these, right? If you look at the oxidation states of our alkenes and alkynes and alkanes, you can see that essentially whether we're converting them alkenes into alkenes or alkenes to alkynes, or if we go from alkanes to alcohols or alcohols to ketones and aldehydes, we're still doing this oxidation and reduction reaction, right? If you look at that oxidation rate of those carbons, it's still being oxidized or reduced accordingly. Okay, so to summarize all of these reactions, I have this table up here just to help you. Again, this might be a good thing to have on you when you're starting to doing practice problems and you're trying to get the hang of your different possibilities for syntheses. So this is probably a good thing to have on a flashcard, for example, while you're studying or doing homework. Okay, so let's try a practice problem with that. And of course, feel free to flip back to the previous slide to help you answer this question. But if we start off with that alkyl halide that you see in the middle, ask yourself, how can we convert it into the aldehyde on the left or the carboxylic acid on the right? Okay, so you could probably, for example, swap out that bromine for an alcohol group, and then you can oxidize it either using a strong oxidizing agent, just using some chromic acid oxidizing agent to get it all the way to this carboxylic acid, right? Because you'd have a primary alcohol, it would oxidize all the way to this carboxylic acid. Or if you wanted to stop at this aldehyde step, you'd use PCC to stop there. Okay, so we've seen ways to extend carbon skeletons. I think a big way to do this was, of course, to use, if you had an alkyne functional group, you could easily do this by converting it into an alkanide ion using sodium amide and and using an alkyl halide to add on carbons to that alkyne group. And then you could always reduce that alkyne down to whatever you needed to. But we've seen in this chapter now, we can use a Grignard reagent to add on alkyl groups. So that's really useful. So especially keep an eye out for any times you have your carbon skeleton extending and there's an alcohol group present. That might key you into, if you're doing a retrosynthetic analysis, you might say, oh, I've got this, if I look at this alpha carbon on my alcohol group, next to my alcohol group, where did that alkyl group come from? Maybe I could use that alkyl group in a Grignard reagent and use the corresponding ketone or aldehyde to make this product. Okay, so something to keep in mind, accordingly. Please note, of course, that with a ketone and an aldehyde, we use just one equivalent of Grignard, and we get, that extra alkyl group. If we use an ester, and we use excess Grignard, we'll add two equivalents of that alkyl group to our carbonyl carbon, and we'll kick off that alkoxide leaving group as an alcohol. So something to keep in mind, again, if you're trying to make a tertiary alcohol that you see over here. Okay, a tertiary alcohol where two of the alkyl groups are the same. Okay, so what if you want to convert an aldehyde into a ketone? Well, we've seen that we can make a secondary alcohol with a Grignard reagent, right? So we start off with our aldehyde, use a Grignard reagent, we make the alcohol. Well, we can then oxidize that back into a ketone, or back into a carbonyl, and now since we've got an extra alkyl group, this is a ketone instead of this aldehyde. Okay, so have a look here. Try and see if you can figure out how you can do this conversion. Okay, so notice that here we've got we're adding on this R group here. So, for example, use this as a you can use that with a Grignard reagent, convert that into a Grignard reagent, and have that attack this molecule here. You would make a corresponding secondary alcohol. But then you could use an oxidizing agent to convert that back into a carbonyl. Okay, and that's it for this chapter. So let's go through some practice problems here. So take a second and go ahead and name this molecule over here. Please note that we've got an alkene as well as an alcohol group. So think about your longest carbon chain that contains both of those and name that accordingly. Okay. And then, of course, you also try to draw this molecule out. I would recommend looking at the latter half of that molecule. We've got cyclohexane diene 1,2-diol. Okay. So I would start off with that cyclohexane, like a 6-membered ring, and then think about where you want to put those pieces. Okay, so you start off, so going with our name, of course, we see we've got our parent chain. We've got 1, 2, 3, 4, 5, 6 carbons that include the alkene and the alcohol group. We start numbering from the left, so that alcohol group's at the 1 position, and your double bond is between carbons 3 and 4. So it's 3-hexene, so that makes it 3-hexene diol, 1-ol. And then we just number and name the other substituents. So we have 2 methyl groups here at the 4 and 5 position, and we have a cyclopentane group or cyclopentyl substituent at the number 3 carbon. With cycloalkyl groups, we alphabetize them with a C. Okay, and with our methyl groups, we alphabetize them with the M. Okay, we don't take into account the di there when we're alphabetizing it, but that's why it's 3-cyclopentyl, 4,5-dimethyl. For this molecule here, again, if you draw that 6-membered ring, where you may have drawn this in a different orientation. I find sometimes it's easier to have the number 1 carbon be at the top here, so it looks like that's what they've done here. They've started at the top and gone clockwise. So this is the 1 position, this is the 2 position, and so we have a 3 So this double bond here is at the 3 position. This double bond, the 4, 5. This is the second double bond, the 5 position. That's kind of what we see here, right? The 1,2 diol tells us that we've got alcohols at the 1 and 2 positions. The 3,5 cyclohexadiene tells us there's 2 alkene groups, and that's where those 2 are. Okay. In the substituent here, we have, this is a dimethyl butyl group. So we have a butyl group coming off here. So 1, 2, 3, 4 carbons. And we've got 2 methyl groups attached to that number 3 carbon, each attached to that number 3 carbon on the butyl group. So it's 1, 2, 3. So there's the 2 methyl groups. As far as stereochemistry goes, that's where the 1R and the 2R come in, and that directs the stereochemistry here. Okay, so depending on, so you can use that to figure out if you're using your wedge or dashed, stereochemistry notations for those groups. Okay, here are some examples of alcohols. Use ARIO to rank them in order of increasing pKa. So in other words, from your strongest acid to your weakest acid. Okay. I think you recall the A in ARIO is kind of a moot point here because all of these have the hydrogen on an oxygen. Okay, so look next for R. Okay, are there any resonance structures? So do we have a double bond position in such a way that that oxygen is in an allelic position? Okay, you've probably noticed that in C. Okay, then look for inductive effects. Are there any electronegative atoms nearby? So you probably notice that in D. We've got a whole bunch of chlorines nearby. And then finally, are there any steric effects that might prevent solvation? So you probably notice that A has some alkyl groups, some methyl groups nearby, so that would probably make it a worse acid. It would destabilize that conjugate base. So A is probably your worst out of all of these. Okay, so you probably see that the order goes C is the best one, then D, then B, and then A. Okay, let's do some synthetic problems. So here we are starting off with a molecule that has a lot of different functional groups. Okay, so I've noticed that we have a ketone over here, we have an ester over here, we have an alkene over here. So with that in mind, look at your various oxidizing agents and ask yourself, what are the products going to look like? Okay, which of these functional groups will get reduced, which ones won't, and what will the molecule look like when these change? All right, and so here are your answers. So notice that with the sodium borohydride, which is a milder reducing agent, it doesn't touch the alkene, it doesn't touch the ester, but it does reduce the ketone into an alcohol, as we can see here. In the case of lithium aluminum hydride, that won't react with the alkene either. So notice the alkene's still intact, but it will reduce the ketone into an alcohol as well, and it'll convert the ester into 2 alcohols. It kind of cleaves that bond and converts this into an alcohol and converts this into an alcohol, as we see here. And then finally, if we use our metal catalyst and hydrogen, that'll convert our alkene into an alkane. We get rid of this double bond here. Okay, so with this product, this molecule, we're trying to design a synthesis, and we want this as our product. It looks like we've got to start off with an alkyl halide and a carbonyl. Now, when you see those 2 pieces, you should be thinking Grignard. Okay, the fact that you're starting off with an alkyl halide, you can convert that to a Grignard pretty easily by just reacting that with magnesium, and then that Grignard has this alkyl group as a carbanion, which attacks the carbonyl and converts it into this alcohol. So with that in mind, look at the alkyl groups that are coming off this alpha carbon on the product you want to make, okay, and think about what those pieces would look like. Okay, and please note that each of those have to have 5 carbons or fewer. Okay, so there's what that would look like. So if you start off with your cyclopentyl bromide here, that has only 5 carbons, obviously. You can convert that into your Grignard reagent by reacting with magnesium with ether as a solvent. And then you can see if we use this as our carbonyl compound, okay, it's got 1, 2, 3, 4, 5 carbons. That provides this part of the skeleton of the product we want to make. Um, you know, this is going to turn into that alcohol group. This carbanion attacks that and forms the product accordingly. Okay. Of course, in that step, it'll only make the oxide. You then have to protonate it using water and mild acid in that last final step. Okay. Again, though, keep in mind you want to use excess of this reagent so that you don't have any leftover Grignard to react with your water and acid. Okay, now look at this molecule and let's go through a multi-step synthesis here. So this is gonna, you're thinking about what the strategies we picked up back in chapter 12, but now we're going to use some of our new reactions that we've learned in this chapter. Okay, so take a second, pause, and think about how you might tackle this problem. Okay, so hopefully you were thinking about how this molecule is changing in terms of functional groups, but also in terms of carbon skeleton. You can see that, I mean, this part of the molecule is kind of recognizable here, but you can see that clearly we extended the carbon skeleton in this direction. Okay, so you want to think about how we did that, okay, and how we can get that to work. Okay, so here's one pathway. Okay, we want this alcohol group to form over here. So if we start off, converting this into a Grignard reagent, we can have that attack this. That can be our nucleophile. You don't have to use your Grignard reagent as a nucleophile on a carbonyl. In this case, by using it with this epoxide, we can get this corresponding alcohol group. So I think what makes the difference here is that sort of carbon that's sort of inserted in between these two. Okay, so this was a kind of a trickier problem. You probably didn't see this one coming because all of the examples we looked at earlier involved carbonyls where your carbanion directly attached to that carbon, your alpha carbon, right? Because it attacked that carbonyl carbon. So I guess this is something else you can also add to your synthetic toolkit there. All right, and that's it for this chapter. So the last problem was a little trickier, based on what we've seen. But again, having that, in your toolkit is not a bad thing moving forward. Okay, but that being said, I think most of the problems you'll see with Grignards involve them attacking carbonyl. So you probably won't see this sort of carbon inserted between where your halogen was and where your alcohol group's alpha carbon is. You'd have a bond going directly here instead, okay, typically. Okay, as always, if you have any questions and stuff, let me know, but please definitely continue to do the homework, try some practice problems out, and and then we'll move on to chapter 14, which will be our last chapter for this semester.